I had to look up wrench sizes earlier. Let me tell you, this ChatGPT is kind of cool because I was looking for wrench sizes. I didn't know what size wrench I would need for something like a bolt. Like I was trying to unscrew a bolt at work today.
Yeah.
And I like literally went into it and I was like, what size wrench will I need? And it said, go ahead and upload a picture of the nut and the bolt if you can. Try to get it in focus. Include something for scale like a coin, a ruler, or your finger. Take it straight on and not an angle. And so I said, okay. So I put my finger on it like that right there. And it said, thanks for the photo. This helps a lot. Based on the size relative to your fingertip and the thin hex nut with the washer, this looks like a common furniture metal frame nut, most likely a 13 millimeter metric or a 1/2 inch standard. And I was like, it sure is. I mean,
it's something. Hi, everybody, and welcome back to this week's episode of From Art to Atoms,
the Ultimate Curiosity Show.
I'm Brandon Shoemaker.
Hey, Brandon. I'm Michael.
And this week we decided to, we got our inspiration while we were doing last week's episode.
Yeah, weird science.
Yeah.
Facts and stuff.
Exactly. So out of that, and, not so much the weird side of things, but just in terms of, how did it even come up? I don't even remember.
We were talking about how Voyager 1 and Voyager 2 have escaped through the very hot heliosphere.
Yeah.
And then we got on the subjects of Voyager and Voyager 1 and 2 and how far they are out. And
so that made us realize, we really need to devote a whole episode just to the Voyager space probes and to really do a deep dive into, what they are and where they came from. And obviously they came from Earth, but the context out of which they emerged, shall we say.
Yep. So we're really going to talk about why Voyager matters.
Yeah. Because, it's a feat. It's the first thing that, humans have made that have traveled outside our solar system.
Well, and I hate saying Voyager because it reminds me of
Star Trek Voyager.
Yeah. Yeah. I'm like, it just feels weird saying that.
And not to be talking about Captain Janeway.
Yes. But in 1977, NASA launched 2 spacecrafts that were never meant to become legends at all. Like you said last week, remember?
Yeah.
They were designed for a 5-year mission.
Well, and hold on, let's back up. Let's give you even more context to that.
Well, we will.
Oh, okay.
We will.
Keep going.
Thank you. This is my awe-inspire moment.
Okay.
They were designed for a 5-year mission, long enough to visit a few distant planets that then quietly just faded into history after that.
Yeah.
They really were. And these 2 spacecrafts were Voyager 1 and Voyager 2.
Mm-hmm.
All right. And 50 years later, they're still alive.
Yeah.
They're still speaking to us from where they're at, far beyond the edge of the solar system. And they've traveled farther than any human-made object ever has, carrying with them not just scientific instruments, but a record of who we are when we first learned how to leave our neighborhood in the universe.
Yeah. And so, that's it's really like if you just take a step back, even, beyond the levels of like nerddom and such, it's sort of a philosophical touchstone, if you will, because it's something that, I don't know, it's hard to describe what the sort of feelings that conjures, because it's not nostalgia, but it's something kind of akin to it, where it just feels sort of like, oh, that's out there and it's going and it's going to keep on going.
Well, I think that, but also it's a story not just about them and the machines themselves, but of human aspiration.
Yeah.
And human, I don't want to say development, but ingenuity.
Yeah.
It's really how people using slide rulers,
are
very, very crude computers.
Yeah.
And just their imagination set these machines out there to outlive us.
Yeah.
They're designed to go out for how many years?
Originally?
No, like now. I mean, they're going to go until.
Oh, yeah. I mean, eventually they'll
go beyond the scope of our solar radiation and stuff like that.
Yeah.
But I mean, they're designed to go out there. They're going to outlive their creators.
They'll outlive us all. Yeah.
They've definitely outlived the people who designed them and built them.
Yeah.
You know?
I mean, really, at the end of the day, they'll probably outlive humanity itself.
Oh, the way we're going.
But anyway, so let's talk about the context from which it came. Or from which they came. You're looking at the late 1960s, early 1970s NASA. So this is when the Apollo missions were winding down. Budget was a big concern for everybody because, just like it is today, but, budget cuts were massive and looming. And also public attention was drifting. And if you think back to when I read that, it made me think of the scene from Apollo 13. You remember Apollo 13? Yeah. So it made me think of the scene where, you've got Jim Lovell and crew up in the Apollo 13 capsule, and they're putting on this show for the nation about, what it's like in outer space. And unbeknownst to them, it's airing to no one except for their families and friends back at NASA headquarters in Houston, that, it wasn't aired for the nation.
Yeah. It wasn't even put on broadcast. They told them that it was, but
and then the networks didn't want it because the interest was not there to give them the airtime for it. So, it always, and I think it's granted, it has to be different, because we weren't alive when man was on the moon. They had already stopped by the time we were born going to the moon. And so, for the people who were around at that time, it kind of became, I think, commonplace, kind of like the way, people going to the International Space Station is now for us, maybe. And so people kind of lost interest in what NASA was doing. So they needed something that was going to be cost effective, something that was going to maybe hopefully stoke some public interest again. And what gets the public more interested than if they have actual images, pictures. And so they realized with this once in 176 year planetary alignment, they had the opportunity to send these two probes out through a gravitational assist, slingshotting them around planets to give them speed and trajectory to explore. Specifically, they were originally going to explore Jupiter and Saturn.
Right.
And so it was just, they were just looking to explore those two planets, very limited expectations. They were going to go take pictures and take some readings and shoot those back to Earth. And then they said, let's make it just a little bit better, just in case. And so that's really sort of how Voyager came to be.
So like Brandon said, in the early 60s, scientists realized that something was going to happen. The outer planets were going to slowly line up. And it only happens, what you said, 176 years? So we're looking at something that, again, will not happen while we're alive.
Yeah.
They realized that with this, though, like you said, they could use gravity as fuel.
Yeah.
To project these things. Right? Stealing just a little momentum from each of the planets to slingshot onward. And we talked about that too last week, didn't we?
Yeah.
What was that called? Angular momentum?
Yeah.
I think. And then I talked about how...
Or at least that's what I guessed it was. And
then I said, oh yeah, well, Captain Kirk and Spock, they went through time.
Oh yeah.
Slingshotting around the sun.
You said that's how they time traveled. I was like, oh God.
Around the sun. Yeah, that's how it happened. So this became known as what they called the Grand Tour, because really you were knocking out 4 planets at once in a single mission.
Yeah.
We missed this window. It's not going to happen again until the 22nd century. Yeah. We're talking about like when Kirk is alive.
Yeah.
According to fiction as it is, So this mission, these spacecraft really exist because someone said, this is about to happen and we need to get on board with this. And it's like you said, we need to use this as a moment of interest.
Yeah.
You know?
So the alignment was Jupiter, Saturn, Uranus, and Neptune.
Right. And no spacecraft at this point had ever visited Uranus or Neptune.
Correct.
Right. And really with that, they didn't know really what they were facing when they sent these guys out there. They didn't know what the atmosphere was going to be like. They didn't know the conditions. They didn't know anything at all. Right. Didn't know about Jupiter's belts, you know, like the rings around Jupiter, what the radiation would be around those. They didn't know what it was made of.
Yeah.
They didn't know that Uranus spins on its side as opposed to our axis of rotation.
Yeah.
You know, and that's kind of weird though, if you think about that.
It rotates essentially backwards.
Yeah.
Compared to everything else.
So does it rotate like this or like that?
It rotates like, well, that
like pole to pole.
That doesn't help people at all.
So
but
it does not rotate left to right. It rotates up and down.
Yes, but at an angle just far enough so that if you look at it in terms of compared to our rotation, it's backwards.
Yeah.
But it's still, yes, it's still rotating on its side from our perspective.
Yeah. And one of the things that they looked at, and this is all coming into what we learned from it, but they also didn't know that Neptune has wind gusts that are actually greater than the sound or the speed of sound.
Oh, wow. Really?
Yeah.
I didn't know that either.
Yeah. That sounds like a dungeon crawler Carl dungeon, like in book 4. That's what it sounds. That's what that reminds me of, some distant world that he's on right now. But we didn't design this for certainty. You know, they designed this to explore it.
Yeah.
So it wasn't built to be smart. And I think that's one key about both of these aircraft, spacecraft, is they weren't built to be smart.
Yeah.
They were built to withstand the unknown. You know, they were built to be resilient. So tell me about the building of it. Do you know about construction and everything like that? Like what we're looking at there?
So the construction happened at the Jet Propulsion Laboratory, which, have you ever been to NASA and seen all that at
no, that's
Kennedy?
I've never been to Kennedy.
Oh, you haven't?
Mm-mm.
You should. It's really good. Wait, now where is the Jet Propulsion Laboratory?
It's not in Kennedy.
That's not at Kennedy. No. Then I haven't seen it either.
I think it's in California.
What is it that I've seen? It's the launch
complexes.
But anyway, so it was built at the Jet Propulsion Laboratory.
Yeah, it's in California.
In clean rooms. So you had to be in tidy whitey space suits.
Yeah, space suits.
To work on them and to work on building them. And they underwent some really extreme testing because, again, they didn't know what all they were going to be facing. So we were talking
really fast. The Jet Propulsion Lab is in a town right outside, kind of northeast of Los Angeles in the mountain area. So it's kind of off of Interstate 210, right north of Pasadena.
I've got to go to LA just desperately. But yeah, so anyway, they were put through extreme testing, extreme vibrations, the vacuum of space. So they put it under vacuum testing, and extreme cold. Because again, space is at absolute zero, isn't it?
Yeah.
Yeah. For power, they used RTGs, which are essentially nuclear powered.
Yeah.
And in terms of computers, they had only kilobytes of memory on board.
Right. Yeah. So these things had basically less memory than a digital greeting card.
Yeah. There was think back to the 3.5-inch floppy days.
Yeah.
You know, it had that, it says kilobytes. So a floppy disk had, what was it? 1.4 megabytes or so, something like that.
Yeah. This is
this is even small. Less than that.
So an RTG is a radioisotope thermoelectric generator.
Yeah, sure. That like I said, it's a type of
nuclear battery. It's nuclear battery that provides long-lasting electrical power and heat by converting heat from the natural decay of plutonium-238 into electricity, making it deep space missions possible where solar power isn't strong enough.
Yeah, that's a better explanation. I knew they were powered by the decay of plutonium.
Yes, so and it's isotope 238.
Yeah,
yeah,
plutonium-238, which is specifically what is used in nuclear bombs.
Yeah.
But anyway, or was, now it's uranium, I think, but Anyway.
And they've used RTGs on several space missions.
Yeah.
Also, let me just say that. But yeah, so these things, they basically had 3 onboard computers running on these little small nuclear batteries that have operated continuously for longer than any computer system in history. Like, we're talking about computer they turned on in the 60s. And she ain't been turned off since.
I was about to say, there is no reboot. There is no, oh, it's not working right. Let's turn it off and turn it back on again.
Right.
There's none of that.
Yeah.
But now that's part of, I think that's also part of the intention behind them being, because they had the capability of making a more complex computer to go on these things. But the simplicity of the computer systems was intended to survive longer, frankly.
And again, that's what we said earlier, that they didn't build it smart. They built it for resilience.
Yeah.
To be able to sustain what's going to happen to it out there.
Yeah.
So let me ask you a question. Why do you think they built two Voyagers? Like, why 2 machines?
Having 2 was, basically it's like having a redundancy system. Anytime there's a major like military operation or something like that, there's
always a backup plan.
They have to come up with a failsafe. And so Voyager 2 was essentially built as that failsafe, in case something went wrong with Voyager 1. Hey, we have a backup. Look at this.
Yeah, but the thing that I have a question about on that is that they had 2 different roles. Like, Voyager 1 was meant to go for Jupiter and Saturn, right?
Correct.
And if it's a failsafe, wouldn't they be doing the same thing, just kind of in case there is one that,
Well, I mean,
what were the roles of each machine or each spacecraft?
Well, yeah, so Voyager 1 was intended to be faster, and it was optimized specifically for Jupiter and Saturn.
Right.
While Voyager 2 took a longer and riskier, more grand tour, let's say, of the planets.
So yeah, I'm thinking that Voyager 2, then if it was longer, it probably went a little bit slower.
Yeah.
And took its time.
Yeah, because Voyager 1 was just looking at Jupiter and Saturn. Voyager 2 was going for
everything beyond.
Yeah.
Yeah. So Voyager 2 is really the one where
like I said, that
did
was
more research, I guess.
Yeah, that it was in-depth research specifically on those 2 planets. And then, with 2, they said, okay, yeah, let's take a look at those 2, but then also let's dive out into Neptune and Uranus, or Uranus and Neptune, sorry.
Yeah. Which one was launched first? Because Voyager 1, you think, I'm assuming they named them as they were launched. Like, 1 goes first, Voyager 2 goes second.
Yeah. They were like a month apart, I think.
Yeah, but Voyager 2 was the one that basically was launched first.
Oh.
Well, they launched it first because think about it. It's going to take its time getting there.
Oh, yeah.
So they had to get that one up there faster, especially if we're looking at the alignment of the planets.
Yeah. So Voyager, so they were named not in order of takeoff, but in order of which would arrive first.
Yes. Yeah. But like you said, so each mission was only supposed to last 5 years.
Right. Just like the Enterprise.
Don't go there. Don't go there.
It's a 5-year mission.
And how many 5-year missions did it have?
Well, the original, it didn't last 5 years. There were only, 3 seasons of the original show?
It did last 5 years.
Star Trek, the original series?
No, it was 3 years, but I'm saying
that's what I'm saying.
The missions lasted 5 years.
I mean, yeah, I know that.
Kirk's missions were the second 5-year mission of the ship.
Oh, and
Pike's was the first one.
Was the first 5-year?
Dude Man, yeah. Christopher Pike was the first one who had the first 5-year mission.
But then Picard and the Enterprise D just had a continuing mission.
Yeah, because their ship didn't have to be refurbed. Yeah, it was basically a community on which it only lasted 7 years. Thank you, Duras sisters.
The what?
The Duras sisters.
Who are they?
The Klingons that blew it up.
Oh. I thought you were talking about a pair of producers that I didn't know about.
No, like the brothers
on the show. Yeah.
No.
I was like, I don't remember them.
No,
I recognize the names of their 3 executive producers.
They're the Klingons that blew it up. Fun fact: do you know the shield modulation of the Enterprise D?
No. What is it? Oh, nerd one.
They're operating on a shield modulation of 214.3.
Thank you.
You're welcome. That just tells you how much I've watched that movie.
Uh-huh. That was what, Generations?
Yeah.
Yeah.
That's when they use Geordi's visor to be their eyes.
Oh yeah, I forgot about that.
And when he first wakes up, they go, "Human females are so repulsive." Ew.
I forgot. Oh my gosh. So yeah, so anyway, we got off on a huge tangent there with Star Trek. Sorry about that.
All right, so but Interstellar Crossing. So we're talking about a 5-year mission, right?
Yes.
They've gone on. That was the expected. Reality is decades.
Mm-hmm.
We're almost, 30, 50 years in?
Yeah.
Okay. Voyager 1 did Interstellar Crossing in 2012.
Wait, let's explain what that is.
I am.
Okay.
Well, you can.
Okay.
Just know that Voyager 1 hit it in 2012, and Voyager 2 in 2018.
Yeah.
Yeah. So what exactly does that mean?
So it means that's when they cross the heliopause, which is essentially, and we kind of explained that on last week's episode too, but that's essentially the barrier of the sun's influence.
Yes.
So
it's where there's no longer an equal
pull. Yeah, that I picked up on.
Yeah. So what the sun is pushing out is equal to, at some point, equal to what is also being pushed into the solar system from beyond.
The interstellar medium.
Right. And so those two are equal at that certain point. Almost creates like a barrier where those two forces are equal to each other. So at one point when you cross that, the forces of interspace medium is going to be greater. Interstellar space will be greater than the sun's beyond that. Yeah. So that's what that means.
So basically, in other words, that's essentially the line that we give for denoting when something is outside the solar system and into interstellar space.
Yes. And if you think about that, that only took about maybe 40 something years. Really? I mean, we're talking about something that happened 5, 6, 7 years ago.
Yeah. Well, no, 2012 was.
Well, I'm talking about Voyager 2.
Oh, well, yeah. But
let me put it in perspective here. That was 2 years before COVID hit.
Yeah.
Like, we're talking like just around the corner.
Yeah.
Time wise, But there's something.
Remember when they thought the Earth was going to end in 2012?
What are you talking about? You remember when they thought the world was going to end in 2000?
Oh, God. Yeah.
All the computers are going to blow up and break down. Are they going to come to life and kill us all?
Well, so you remember what the argument was in 2012, why they believed that was going to be the year that the Earth ended? Do you remember?
No.
It was because the Mayan calendar ran out in 2012. Gracious. I'm like, but isn't it much more logical to realize at some point, dude man who was making the calendar died?
Talk to me about this golden record, please.
Sorry.
Talk to me about the golden record on the Grand Tour. What's the golden record on the Grand Tour?
Yeah. So, and what's interesting is, so the golden record was not planned initially. Carl Sagan was actually the person who kind of spoke up and said,
well, okay. So who is he?
Oh, Carl Sagan was a cosmologist who was known as he was kind of like the Neil deGrasse Tyson of his day.
Okay.
He was very well known. He was an astronomical expert, but he was also very much in the pop culture eye.
Okay.
He was the narrator and the host of several science series and stuff like that. And he was also the author of the novel Contact, which was made into the movie with Jodie Foster. We've talked
about that because that was one of our
favorite movies.
Yes, from season 1.
Yeah. So, so Carl Sagan, big damn deal, basically. But he is the person who spoke up and told NASA, we need to include something on there that says who we are. He said, we're sending this thing out and it's going to keep on floating. At some point, long after its mission is over, we're not retrieving this thing. And so it might be discovered at some point.
I was going to say, what's scary about it, though, is that they expect this thing to run out of power in, how many years? This battery is going to live for about 100 and something years. We're expected for it to live, 200 years. They expect this thing to keep on going.
Yeah.
Like, eventually it's going to go quiet.
Yeah.
And that's just, they put this quiet little golden record on there praying that whoever finds it will be able to understand it.
And we'll have a record player.
I mean, you're not wrong.
I mean, because
Well, hold on. So no, but
the golden record, the intention was to
not be played on a record player.
Yeah, I know. Well, how is it supposed to be played then?
It's not designed to be found. It's designed to matter. Like they have geometrical and scientific. It's not played. It's in the shape of a record, right? But it's not actually like you turn it on a turntable and you press play and it plays sound waves off of.
No, it does. It contains It contains recordings of greetings in 55 different languages.
Well, maybe there's like in contact, maybe there's instructions somewhere that tell them how to build a record player, which is coming back retroly now. So,
I mean, this is true.
Hold on. I'm gonna look it up real fast. The golden record in space or in Voyager. Okay. The golden record is a gold-plated copper phonographic record launched on Voyager 1 and Voyager 2 in 1977, serving as a time capsule message to ET life.
Mm-hmm. Extraterrestrial life.
Containing Earth's music, like Chuck Berry and Mozart.
Mm-hmm. Mozart.
Yeah, but they don't have Lady Gaga on there. Come on, man.
Well,
let's launch a new one.
She wasn't born yet.
She was born in 1977. How old is she? She younger than us?
No, I think she's like around our age.
Anyway.
Hey, Alexa, how old is Lady Gaga?
Lady Gaga is 39 years old.
Oh, she is younger than us.
Yeah, she's not. That would be like 86.
Something like that. She is definitely not a zennial. She is 100% a millennial. Let's put it that way.
And that's why she's not on this golden record right there. But it has greetings from 55 languages and 116 encoded images, photos, diagrams of space, anatomy, all selected by a committee led by
Carl Sagan.
To portray humanity and life on Earth with pictographic instructions for playing it in the vastness of space. So there are instructions on how to play this thing.
But they're going to have to figure out how to build a record player first.
Look.
You'd think they would toss one on board.
So wait, so it has Bach, Beethoven, Chuck Berry's Johnny B. Good, music from China and India.
Oh God, you remember that incredible scene from The West Wing where Josh is sitting in his office and CJ comes in and he's listening to, I forget the artist's name, the blues player who was blind.
I don't know.
And he's listening to him and he says, this man was blind, died penniless in the street or whatever, but his music just left the solar system.
Yeah.
Kind of makes me choke up even repeating it.
That guy.
But yeah, I feel bad now for not knowing his name.
Well, it has music on there, but it also has nature sounds like thunder and waves.
Yeah.
Animal calls, human
birds.
Sounds like laughter, footsteps, a kiss, and a 90-minute music selection, which has the music in there. It also has 116 encoded images showing human anatomy, daily life, scientific diagrams like DNA, equations and planetary locations, and spoken greetings in 55 languages, plus messages from President Jimmy Carter and UN Secretary General Waldom at the time. How does it work? So you ready for this? Is the instructions.
Oh, is it? Okay, yes. This is what I want to hear.
Decoding it. So pictographs show how to play the record using a stylus and a cartridge, which was also included.
Oh, okay.
And the location and time uses the hydrogen atom's spin flip transition for time and a pulsar map to locate our solar system. So it tells them
where it came from. Yes.
Right. And then designed to spin at 3.6 seconds per rotation for playback. So it gives them how fast it has to spin.
Yeah.
And I'm just sitting here thinking, who in their right mind thinks that these extraterrestrials are going to be like, yeah.
What do you mean? Yeah.
What would we do if we found something like this from some distant planet?
Oh, you know what I would do? I'd figure out the directions and do it.
Yeah, that's what happened in Contact, and look what happened there.
Yeah, she went on this incredible journey and spoke to an alien in the form of her father.
That's not true. According to everybody else, she flipped right through.
Well, that was because of, but yeah, what concerns them was the fact that the static
recording
that she recorded was approximately 14 hours of it.
I understand that, but again,
She's still got a healthy grant, thanks to Miss Angela Bassett.
that is true. I need to go back and watch that movie.
I do too. I want to now.
That's one of our favorite movies.
Well, especially when we get to the pale blue dot.
Oh my goodness. Okay. So, so Voyager is just proof that exploration is not about where we're going to go. It's about what we choose to carry with us and how far we're willing to send it. So the spacecraft itself, again, it's going to keep on going, drifting between the stars long after the Earth has changed beyond recognition of what it is today.
Mm-hmm.
Voyager 1 and Voyager 2 are not just spacecraft. They're time capsules with this information that we put on it. They're ambassadors to our planet and reminders that curiosity is one of the most durable things humanity has ever built. And I feel like we've lost kind of a lot of that.
Oh, yeah.
Like when you were saying there's very little interest in space back then in the 60s, right?
Mm-hmm.
And it's so commonplace, like Apollo was so commonplace at that point, going to the moon was like us sending people to the space station.
Mm-hmm.
But the problem is, and I know that our lack of going to the space station is because we retired the shuttle fleets, and are waiting for Artemis to.
Well, we're still going to the space station. We're just hitching rides with the
That's
Soviets.
the thing, though.
The Soviets. Oh, my God. The Russians.
Right. But you don't hear about that in the news. It's not newsworthy anymore. Anything space is not newsworthy. You never hear of that kind of stuff anymore.
Yeah.
And you and I kind of both agree on a lot of things dealing with this, is that we've lost our sense of exploration.
Oh, yeah.
We're so focused on here on this planet,
mm-hmm.
the territorial stuff, the small
mm-hmm.
things that don't really matter at the end of the day to humanity's purpose.
Yeah.
That we are losing our exploration, which really could drive humanity to evolve more and beyond what it is.
Well, yeah, because if you think about back in, go all the way back to the discovery of the Americas,
mm-hmm.
We had a sense of exploration then, and it drove us to find these new worlds, these new lands,
Were we really looking for new lands?
Well, no, we were looking for a quicker
Salt.
route to
we
the
wanted
Indies,
spices.
But
something to make our food taste good.
Yeah. But
maybe we haven't found that in space yet. Maybe we should.
Oh, but remember, space tastes like cotton candy.
Oh, yeah.
Yeah.
According to Coca-Cola, it does.
Well, not just Coca-Cola, according to science.
Yeah, remember when the Coke had that flavor come out?
Yeah, I
was
forgot
it 2
about
years
that.
ago, whatever like that? Yeah. And that's what it tastes like.
Coke. Yeah.
Yeah.
Well, because they kept, but that was genius marketing, because scientists had come out saying, the outer space tastes like cotton candy, and Coke said, well, here's an outer space flavored Coke.
But if you think about that, then so what is cotton candy? Pure sugar.
Yeah, with some flavoring in there, I guess.
Right, but
I want cotton candy.
Anyway, but if that's pure sugar, what is the molecule of life?
Carbon.
That's an element, not the molecule.
Oh, molecule. Sorry.
What do you need to survive? What to live? Carbon's what you're made of, but what is one thing that we need to survive?
Glucose. Fructose,
which is
sugar.
There you go. And what is your DNA made of?
Acid. Nucleic acid.
Right, but the backbone is made of.
Wait. Don't tell me. wait. Don't tell me. Tell me. Go ahead.
Okay, let me ask you a question. This is how you know what it is. Think about what sounds familiar in these words: glucose, maltose, fructose, sucrose.
All of them.
Right, but what part of the word sounds familiar or is common in all of them?
Oh, so they're all sugars.
Right, so that's how you know, right?
Yeah.
Okay, so RNA is called ribonucleic acid.
Oh, I never knew that it was short for ribose.
Yes, and DNA is deoxyribonucleic acid because it's also made of deoxyribose. Which
I've
is what?
never known that.
Which
a
is
sugar.
what?
I didn't know that.
The backbone of DNA is made of a sugar, phosphate, sugar, phosphate, sugar, phosphate, sugar, phosphate. Your DNA is made of sugar.
Well,
bless my soul.
I was about to say something far worse.
Mike's on the roll. Every living thing's DNA is made of sugar backbone, sugar phosphate backbone.
I have never heard the full term ribose.
Yeah, it's ribonucleic acid.
It's made
of ribose sugar, phosphate, and nucleotide, or a nucleic base.
I've known deoxyribonucleic acid and ribonucleic acid, but
That's
I didn't know what the ribo was on its own other than ribo.
Yep. Nucleic acid is made of the sugar deoxyribose.
Okay. Well,
Yep,
they
Franny.
literally mean it when they say you learn something new.
I was ready.
day.
You ready? Look, the more you know. Boom, 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 boom.
Okay.
So
anyway.
I mean, really though, the molecule of life is sugar.
Yeah.
Like you're made of it. You need it. You will not survive without it.
Yeah.
Right. And so it's kind of odd that whoever, the grand scheme of things, that outer space is and tastes like, smells like sugar. And we do come from the outer space.
That is okay. That's really cool. Okay, so let's. Are we going to actually talk about what?
Yep. So let's talk about each of the individual spacecraft themselves. So I think you were going to cover Voyager 1's kind of like what its mission was, you know?
Yeah.
Okay. So you want to go for Voyager 1 and I'll go for Voyager 2?
Sure.
Okay.
So Voyager 1 launched on September 5th, 1977, my birthday. So 4 years to the day before my birthday, Voyager said, "See you later." And so its original mission was pretty conservative by today's standards. It was a flyby of Jupiter and a flyby of Saturn, specifically to study their atmosphere, their moons, their magnetic fields, and their rings.
Mm-hmm.
And the mission duration was supposed to be just a few years. That's it. There was no ambition for interstellar travel. It was never intended to be the farthest object sent out by man in the universe.
Right. It was I don't want to say unexpected, but just kind of a perk.
Yeah. Oh, yeah. And it wasn't even supposed to be the long haul champ. That was supposed to be Voyager 2, like we said earlier.
Yeah.
Voyager 2 had the much bigger itinerary. And the path of Voyager 1 was chosen because it gave the best angle on Saturn's moon Titan, which scientists were desperate to study back then.
Right.
So that decision is kind of what changed everything. Jupiter, although, is where it really sort of shocked everybody. Voyager 1 reaches Jupiter in 1979 and immediately ruined science textbooks across the world because it discovered that Jupiter's moon Io is volcanically active, which was the first time that active volcanoes were observed outside of the Earth. There were massive sulfur plumes erupting hundreds of kilometers high, and it proved tidal heating is a real thing. It observed that Jupiter's atmosphere was comprised of a complex system of storms. You know, if everybody's heard of the big red spot on Jupiter, that is actually a supermassive hurricane that is in constant rotation around Jupiter.
Hey, you know what else?
What?
Fun fact. What else was found in the big red spot of Jupiter?
What?
The last Borg cube. To quote Will Riker, they're hiding a transwarp conduit in Jupiter?
When was that?
Picard last season, season 3.
Oh, okay. Did I watch that season?
Yeah, that's where it was. That was in the episode 10, The Last Generation.
Oh, where
they discovered that the Borg cube was inside after fleet formation was turned on, and they've used Jack now to communicate and turn everyone under like 25 or 35 into Borg.
I need to go and watch that again. I don't remember any of that.
Really? Yeah.
Jack's Picard's son, right?
Yes.
Yeah. Okay. I want to make sure I was at least following that closely.
Yes.
So back to Jupiter's atmosphere.
Okay, go.
The Great Red Spot. Jupiter also had supersonic winds and turbulence far beyond anything imaginable. So imagine if you were flying a plane through those winds on Jupiter.
I can't imagine that because they're beyond anything imaginable.
And then on the moons, Europa, another moon of Jupiter, showed signs of a smooth, cracked, icy surface and it gave early hints of a subsurface ocean, which wasn't confirmed then, but the seeds were planted for that theory.
Mm-hmm.
Two other moons, Ganymede and Callisto, were revealed to be geologically complex, not just dead rocks.
Okay.
And so basically it turned Jupiter from, what we knew of it at that point as just a big striped ball into a fully functioning planetary system all of its own.
Yeah.
Which is something that was something that 2010, the year we make contact,
Mm-hmm.
the sequel to 2001: A Space Odyssey, that was something. Have you ever seen that one?
I don't want to say anything right now because you're going to hit me.
Okay. You haven't seen either one of them, have you? God. Okay. 2001 is just a mind.
That's Spielberg.
No, it's, oh my God. The Shining, Eyes Wide Shut.
Is that Jack Ruber?
No, Stanley Kubrick.
Okay. I got
Stanley
last
Kubrick.
name. I got last name right.
2001 is hard to understand because it's kind of just like a psychedelic trippy type thing.
So is Xanadu. Let me tell you.
Xanadu.
Yeah.
Ugh. You watched Xanadu?
I didn't understand it because I wasn't,
Oh,
trippy.
anyway. So 2001, 2001 is very confusing. 2010, the year we make contact, is much more accessible as a movie overall. But anyway, that's one of the things that movie explores is the potentiality for Jupiter to become a star.
Mm-hmm.
And so in the movie that happens, and then we become like a binary system. But really, if you think about it, it is practically like Jupiter is its own little planetary system.
Yeah.
Given the diversity and number of moons that it has, for that matter. It's got more moons than the sun has planets. So, and then
when you think about how our moon was formed,
mm-hmm.
does that mean that Jupiter's moons were formed the same way?
Oh, God.
That it was like hit, you know what I mean?
You're taking me back to College Astronomy 101, which was the very first class
I never took that.
Stepped into in college. You didn't, of all people, you didn't take astronomy?
No, because I was on a biology track.
Yeah.
So most of my courses were embryology, anatomy, phys, animal behavior, stuff like that.
Oh, well, I was a communications major, so I just had to have an elective science, and I was like, astronomy, sign me up. And then I was so pissed because they were supposed to have the lab, which would have been like actually, going out and using telescopes and stuff. And then they had to cancel it because they didn't have somebody to teach it. Oh, I was so mad. But anyway, so I had to take a different science later on so that it was a lab science. But anyway, I still took astronomy because it was astronomy. But anyway, I know there are 3 different methods for moons to form, or theories for how moons form around planets. And I can't remember what all 3 of them are. One is that
collisions.
Yeah. And it's like a chunk off of the planet. Mm-hmm. Others is like an accretion disk of matter around the planet during its formation, where it was
pulled into the surface, but it was kind of just
it was far enough away so that it wouldn't be pulled into the surface. But basically that's what happens. That's how rings form, is where rocks weren't traveling fast enough or whatever to coalesce into a moon.
Yeah.
But they weren't close enough either to be pulled into the planet itself.
Yeah.
And so moons form. Anyway, huge sidebar there. Sorry.
But that's what people come here for.
What?
The learning sidebars. They're the educational sidebars.
Of course. I was like, come where? I don't know where we're talking about.
They come here to listen to
First,
us.
I thought you meant Earth.
No. Very limited educational sidebars there.
Yeah. So then it goes and has its look at Saturn. So Voyager 1 arrived at Saturn in 1980.
Okay.
And this is where it made history by not going somewhere.
So 3 years, basically.
Mm-hmm.
Didn't take it long at all.
Yeah. In the grand scheme of things, yeah. So the rings of Saturn, it found that the rings are not solid sheets of ice and rock, but are complex systems of particles. It revealed in the rings gaps, braiding, and shepherd moons, which are, where chunks started coalescing, but didn't fully form. And then it showed that Saturn's rings are dynamic and structured. It's not just like what we think of in terms of
just kind of floating. There's actually, like you said, there's a whole, I
there's
won't say ecosystem, but there's a whole design,
a complexity to it. Yeah. Almost like, obviously on the macro scale of this, but almost like in my mind, at least, it's kind of akin to like the structure of a snowflake. How incredibly intricate and complex that is.
Right.
And then Titan, the moon of Saturn, it discovered that Titan has a thick nitrogen-rich atmosphere. It has complex organic chemistry, and its surface is completely hidden from view. So Titan fascinated scientists, but the close flyby required Voyager 1 to tilt its trajectory sharply. And so what that did was it gave us really valuable data on Titan. And in doing that maneuver, it's also what ejected Voyager 1 out of the plane of the solar system. So this meant it would not be going to Uranus. It would not be going to Neptune. It was just a straight shot toward deep space. So Voyager 2 got the Grand Tour, and Voyager 1 got Eternity out into outer space. And then finally, in 1990, long after Voyager 1's planetary mission was over, once again, our good old friend, Carl Sagan.
I thought you were going to say Luca.
Our good old friend Carl Sagan pushed for Voyager 1 to turn around one last time. And so in doing so, from over 6 billion kilometers away, Voyager 1 photographed the Earth.
Okay.
And in this photo, and we'll put this up on the Instagram, in this photo, Earth appears as a single pixel suspended in a sunbeam. And the photo became known as the pale blue dot. And Sagan's reflection became legendary. And you can look that up online and read it. He wrote a whole little, not poem, but it kind of looks like a poem titled The Pale Blue Dot. But it's really just a reflection on the photo, the image itself. But this picture became significant and timeless because it reframed space exploration as a human story. It turned a data gathering probe into now a philosophical artifact. And it permanently altered how we talk about Earth's fragility. Because here's the thing that you have to consider, in this image that shows the Earth as just one pixel, think about it in these terms. That dot contains every human who ever lived and whoever will live. And Voyager took this photo while already leaving us far behind. So, and that's what brings us to, Voyager's final, really, I guess, its reframed mission. Because like you said, since it is still going, we're still getting data from it and everything else. So, at this point, it's just a matter of, let's just see how far it goes. And so after Saturn, Voyager 1 entered what's called the heliosphere, like we've talked about before, the bubble of space that's dominated by the solar winds of the sun. Some key milestones for it. In 2004, it crossed the termination shock, which is when which is where the solar wind slows down. In 2012, that's when it entered interstellar space, like we mentioned before. It detected several things: a drop in solar particles, an increase in cosmic rays, and a change in magnetic environment. So we know that interstellar space versus the space within the solar system in which we occupy, we know that there are these differences in, the magnetic environment, the cosmic rays that are, because think about all the things that, interstellar space is bombarded by, gamma rays,
right? Right.
that are just fired off in any random direction. Like I remember when I first learned about, you know, stars and novae and things that release gamma rays just like a random bullet, you know, shot in a given direction.
Mm-hmm.
You know, I was like, oh my God, you know, and some of them are pointed right at us. But, you know, it's the heliosphere and things like that that protect us from those rays. So, and now it's also important to make the distinction. Interstellar space doesn't mean outside the galaxy. Okay. It's still very much in the Milky Way. Okay. But it's no longer in the sun's neighborhood, so to speak. What Voyager is doing right now, it is over 15 billion with a B miles from Earth. Signals from Voyager take more than 22 hours one way. So if we can still give it signals and commands and things like that as well, but it takes 22 hours for that signal traveling at the speed of light to get to it, and vice versa when it's sending data back to us. And, you know, like we mentioned earlier, is powered by the radioisotope thermoelectric generator, the RTG, and is literally running on fumes.
Mm-hmm.
But those fumes, again, are going to last for how long did you say again?
But I mean,
more than hundreds of years.
Yeah.
Yeah. NASA is slowly shutting down instruments on Voyager to conserve power. Eventually, communications will cease and Voyager 1 will go silent, but it will continue drifting for billions of years to come.
Mm-hmm. Until it's hit something, basically.
Yeah, until it's hit something or something finds it.
Yeah. And I know that in designing these things, they were meant to take micro impacts.
Yeah.
Without it destroying or anything like that, or impacting the mission itself.
Yeah.
Like I said, they were designed for longevity and for resilience. So micro impacts, they knew micrometeor impacts were going to hit.
Yeah.
You know. So Voyager 2 is the only spacecraft to visit all 4 of the giant planets.
Yeah.
Right. So Voyager 1 kind of got the shaft. Sorry. Voyager 2 was never designed to be the backup.
Yeah.
Voyager 1 was.
Yeah.
Which is weird.
Mm-hmm.
You know, 2 was launched first because it was going to hit all 4 of the planets. It was going to go on the longer, more complex, riskier trajectory of the alignment of those planets.
Yeah.
You know, and that's one reason why I think, like I said, they had to launch it first because they had to get it going.
Yeah.
They had that kind of time bubble.
Well, yeah, know. And I feel like Voyager 1 was meant to be sort of like a specialist.
Yeah.
You know, focusing specifically intensely on Jupiter and Saturn.
Right. So, but with that said, knowing that the path was going to be longer, we were hitting more planets. They had to understand that it was going to be exposed to more radiation. There was a bigger chance for failure, and that there would also be a greater scientific reward come out of it. You know, and so it had 3 overarching goals for their mission for Voyager 2. Explore the outer planets close up, test gravity assist navigation on unprecedented scale, and collect data that could not be obtained from Earth-based telescopes.
Yeah.
Okay. We start with the Jupiter flyby. So 2 years into this mission, the closest approach to Jupiter was in July of 79. And Jupiter was really the first real test of this spacecraft. And like you said, this one confirmed that there were volcanic eruptions on Io, you know, on the moon. It looked at the radiation environments of Jupiter itself. It mapped out the storms and the bands, the cloud bands, and measured its magnetic field. So Jupiter could only have ended this mission early should the radiation belts, have been so intense that it would have damaged the electronics on it. Like it could have been the end of everything right there for this one.
Yeah.
But it didn't. It didn't. And she continued flying on to Saturn, which is in 1981, again, 2 years later. And how long is it going to take us to get to Mars?
Fred, you are an Earth crew?
Yes.
I think it's 3 years.
So I'm sitting here thinking, looking at these time missions, you know, 2 years to get from Earth to Jupiter. And I'm like, why is it going to take an extra year
for us to go
a
not
manned
as
mission?
far. Yeah. I wonder why. I mean, because you're in outer space. It's not a matter of like
mass,
we can't handle
or
that.
weight.
Yeah. Or us not being able to handle that speed.
Right.
Are
you looking it up?
Yep.
So while he looks it up, we're going to talk about Saturn some more. We're going to do a flyby of Saturn in 81. And we're looking at almost a little over 2 years. So August of 81 is our closest approach. And Saturn was both a scientific target and a decision point. While Voyager 2 was kind of looking at Saturn, we got high resolution images of Saturn's ring, identification of ring gaps and new moons, and we also were able to measure its atmospheric and magnetic sphere. And after Saturn, Voyager 2 was cleared to continue onward to Uranus and Neptune. So everything beyond Saturn depended on Voyager 2 still being healthy. And luckily for us, it was. So in 1986, again, we're 4 years later now, in January of 86. And I find this one kind of interesting also because the closest approach hit at the exact same time that the Space Shuttle Challenger exploded.
Really?
January of 86.
Oh, wow.
So this was the first and only spacecraft ever to visit both Uranus and Neptune, so Uranus rotates, like Brandon said earlier, on its side with about a 98-degree axial tilt, which you think a right angle is what?
90.
There you go.
So you've got 8 degrees that pushes it past to make it backwards.
Yes. Yeah. Yes. It has a magnetic field tilted to offset the planet's center. It's extremely cold. Low contrast atmosphere, and we found new moons and rings around Uranus also. Why Uranus really kind of is special is because everything we thought about it based on other planets is exactly what it wasn't. Because like you said, it rotates how?
In reverse.
Backwards, yeah. Right. The magnetic poles were not aligned.
Yeah.
Seasonal extremes were unlike any other planet, and the internal structures challenged every existing model we had on planets. And so it forced us to admit how very little we actually knew about ice planets, ice giant planets, I should say. And so, this spacecraft is kind of really making us not only learn things, but kind of like realize just how much we don't know.
I was about to say, rethinking our assumptions.
Yes.
Yeah.
And so we're going to talk about the last and grand finale in 1989. Again, 3 years later.
Real quick before you do that, I just wanted to say, we dumb. It only takes 6 to 9 months to get to Mars.
Okay, well.
That makes a lot more sense.
Yeah, it does. It does.
We stay in the International Space Station much longer than that. What?
I'll be at my house longer than that.
Oh, yeah.
I mean, let's launch right now. We'll be there by summer.
Yeah.
It'll feel like it when we land too, let me tell you. So Neptune's flyby in August of 89, it was the first and again, the still only man-made object to visit Neptune. Here we go. You ready? So the winds exceed at Neptune. The winds exceed 1,200 miles per hour.
I just had a visual image of standing in wind like that.
You're going to look like those little hurricane reporters on the Weather Channel.
Literally, like you're standing, then it starts.
Yeah. I mean, it's going to peel your skin off.
Yeah.
Your skin will fly off of your body. It has a warm internal heat source. There's active nitrogen geysers on Triton, which is one of the moons. And that it was the final planetary encounter of the Voyager program. So this is really the last time one of these spacecraft is going to be around a planet.
Yeah.
And it is the first close-up look at the most distant planet that we've had. So Voyager 2 turned Neptune from a mathematical point into something that was living. We were able to get, it was no longer just a dot.
Yeah.
We were able to get research from it. And so after 1990 to now, Voyager 2 has become interstellar. It's entered a new mission to where we're looking at the outer edge of the sun's influence at this point. And again, in 2018, it crossed into the heliopause, become the second spacecraft ever to enter interstellar space. Can you name the first spacecraft that entered interstellar space?
Voyager 1.
Yeah, ding, ding, ding. Yeah, okay. So what exactly is Voyager 2 doing right now? Well, it's measuring plasma density, it's measuring magnetic fields, And it's also looking at cosmic rays beyond the sun's reach. So unlike any other probe, number 2 provides direct measurements from outside our solar system. So a little bit of fun facts there. Engineers have carefully shut down systems to conserve power, but how long does it take for commands to get to Voyager 2 and then back again?
Well, since it's 22 hours for Voyager 1, I would say a little bit less since it's not quite as far out yet.
Mm-hmm.
What, 18 hours?
Yep, 18 hours.
Oh.
Yeah. Yep, 18 hours. So Voyager 2 is proof that careful planning, humility before the unknown, and durable curiosity can carry us further than raw power ever could.
And now the thing that I find so interesting about this is that, you know, we've sent many other probes to planets since then.
Mm-hmm.
But think about how they're designed. A lot of them have failed.
Yeah.
You know, but a lot of them also are designed not to slingshot around the planet or anything. A lot of times they're designed to crash into the planet.
Yeah. I mean, think of like the Mars Curiosity and the rovers and stuff like that. Like that was their plan.
Yeah.
I mean, to crash into
well,
it
granted,
because,
the rover,
right,
so that it could get off
explore,
and ride around. But
right. But the thing is like these spacecraft were designed strictly just for research, you know?
But I just think that's interesting that these are the only two that have, you know, with very rudimentary, by comparison, very rudimentary computer systems and things like that. But yet they're the ones that have gone out there and
okay, so Voyager 1 is moving onward from the plane. Direction is the fastest human-made object ever launched from Earth. Right now, currently, it is traveling at around an estimated 38,000 miles per hour.
38,000 miles per hour. Now, talk about running past the speed limit.
Okay, we'll talk about winds going 1,200 miles per hour.
Yeah.
Voyager 2 is, again, slower.
Yeah.
It was. But it says slightly slower at just around 35,000.
Oh, only 35,000?
Only 3,000 less.
Oh, I can catch that at a jog.
Hold on, let's break these speeds down.
Yeah.
If you could travel at 38,000 miles per hour, like Voyager 1 is,
yeah,
you could travel from New York to Los Angeles in 4 minutes. You could circle the Earth in 38 minutes.
How fast does the International Space Station travel? Orbit?
So I'll tell you, even at these speeds, Voyager is going to take tens of thousands of years to reach another star.
Yeah.
And it's going to take just around 40,000 years to pass near another star system, Gliese 445.
Wait, what? 445?
Yeah, Gliese, the star system, Gliese 445.
Oh, I thought you said at least 445.
No.
Okay.
Gliese.
Gliese. Sharon Glass.
Yeah, we're going to name those two stars Cagney and Lacey.
Okay, the International Space Station. I knew it was pretty quick, but not that fast. The International Space Station rotates around the Earth at around just over 17,000 miles per hour.
Oh, so still faster than the speeds of our moon.
Yeah.
Is it Neptune's moon? What did I report Neptune's moon had the
the wind?
Yeah.
Oh, yeah.
Yeah, it was Neptune.
1,700?
Yeah.
Something.
It was 1,200.
1,200.
Yeah.
Okay. Yeah, I knew, things traveled pretty quickly because I knew they rotated around not once an hour, but something close to that, which would be because that's a little slower than half the speed of Voyager 2, at least, I think. So,
all right.
So what are your takeaways? What are your final thoughts on the Voyager space probes?
I guarantee you I can run faster than these things are going.
What?
I can run faster than these things are flying.
Sure, with a jetpack and the medium of the solar system out there in outer space.
Yeah, I'm gonna get my flash suit on and zoom.
There you go. Sure. Okay, Sheldon.
That was on tonight at the gym.
I know. I saw it.
I told Thomas Roger's going to come in as Aquaman. Give it a second. And he goes, what? And I'm like, look, there it is. It was one of the best episodes ever.
Yeah.
My takes on this is, it's very strange to think that these things are going to continue on way after humanity's gone.
Mm-hmm.
And in the grand scheme of things, they will continue on as something that humans actually once touched.
Mm-hmm.
is that far out and that distant now. It's just kind of like we litter in interstellar space.
Well, yeah.
I mean, we've thrown our space trash out there, but it's just something to think about when you think of like, it puts our lives in perspective. It puts humanity in perspective. It makes us realize that we're super, super small.
It does. And then it also, keep in mind, it does keep us in perspective as well. When we get wrapped up in our own lives so much, and we think our problems are so huge, especially, when we talk about first world problems, we get so wrapped up in them. And at the end of the day, in the grand scheme of things, we are so insignificant. The comparison is often made like, oh, it's like we're just a bunch of ants on the seashore or something like that. But it's even smaller than that because it's infinitesimal. I can't say that word. It's smaller on an infinitesimal scale. There we go.
So are my bills. So can I stop paying them so I can just explore?
I mean, if you don't care about the IRS and people coming after you.
Who's going to come after me?
I know, right?
As long as I can explore, I don't care.
Well, but then
it makes me think about my life. Like I have one life to live on this planet and I'm wasting it working instead of just enjoying it.
Oh, yeah.
Who is the man that set this thing up?
Capitalism.
Henry Ford.
No, Alexander Hamilton. Blame him. It really is. It's his fault. But no, I think, for me, I do believe in extraterrestrial life, and that something is out there. Now, granted, is the likelihood that one of those life forms are intelligent enough to observe one of these space probes flying by and capture it and see it? Who knows? Again, I mean, it's going to take how many years again to get to the nearest star, let alone find one with intelligent life. Yes, that's an extremely distant potentiality. Okay.
Mm-hmm.
But still, the fact that it's out there, that it is a potentiality for it to be discovered by somebody or something out there. And to know that, we've sent this out and said hello in 55 different languages, none of which they will speak, but it's okay. Similar to your observations on it. It's something that is it's something important, for us to have done just for the sake of having done it. And, for the sake of the potentiality.
Yeah.
All right. You got the trivia book in your hand. You ready to go?
Yeah. Are you ready? I'm not letting you pick this time. I'm picking your own category.
I could tell since you already have
turned
to a page.
Let me get my light on.
Get your light. Get your light going, Grandpa.
Okay, I'm gonna give you this one. You ready?
What's the category?
Music.
Oh, okay.
Mm-hmm. Okay. Heartbreak Hotel is a song by which iconic singer?
Elvis.
Okay. Who is the lead singer of The Smiths?
Oh, crap. His name is escaping me.
Mm-hmm.
I can't. What is it?
Morrissey.
Yeah.
The Beatles' All You Need Is Love began with what piece of music?
Hold on. I'm listening to it in my head. Hang on. I can't recognize what it starts with though. What is it?
The French national anthem.
Oh, yeah. Okay.
Who wrote the operas The Magic Flute and The Marriage of Figaro?
Oh, Beethoven? No, Mozart.
Yep. And this one, you'll know this one. The movie Back to the Future featured a song entitled Back in Time by which band?
Huey Lewis and the News.
Yep, there you go. Okay.
What category you want? Or you just want me to pick?
Yeah, just pick one.
Okay, I'm going to do movies. Okay, you'll struggle, but I'll help you. All right, number one, what 1992 horror movie remade in 2021 was directed by Jordan Peele?
1992 horror movie.
No. Yes, sorry.
Remade in 2021?
Mm-hmm.
Texas Chainsaw Massacre.
No. Think urban legends.
Candyman?
Yeah. All right. Number 2, Robert Mitchum acted in the 1960s original and Robert De Niro in the remake in 1991. What was the title of both the movies?
Okay. Who again?
Robert Mitchum in the 1960s original and Robert De Niro in the remake in 1991.
That's all it gives me?
Yeah. What was the name of the movie?
That Robert De Niro played in, that this other guy also played in. The original. The original.
Uh-huh.
I have no idea.
It's based. The title is a place name in North Carolina, out by the coast.
I have no idea.
On a cape.
Again, I have no idea.
Cape Fear.
Okay, I was gonna say.
In Star Wars, who killed Qui-Gon Jinn? You don't know who Qui-Gon Jinn is? Liam Neeson's character.
In the original Star Wars or in their prequels?
There was no Qui-Gon Jinn in the original.
Oh, he was what's his name's mentor? He was the original.
Uh-huh. He was Obi-Wan's mentor.
Who killed him?
Yes.
Like the character name or the actor name?
The character name.
Oh, wasn't it like Darth or the Emperor or somebody?
Darth something, yeah.
Darth Maul.
Yes, there you go. Good Lord.
But Darth Maul came in the prequels.
That's what I said. Qui-Gon Jinn was dead before the original.
That says in Star Wars, does it not?
Yes.
Not Star Wars.
In the Star Wars universe.
Okay, does it say that?
No, it says in Star Wars.
Well, that's different than Star Wars is a movie title.
No, but if that were the case, they would say Star Wars: A New Hope.
I'm just saying.
In the 1999 version of The Mummy, what is the mummy called?
Oh. He has a name? Is it not just the mummy?
Yes, he has a name, but I clearly looked at the wrong answer because I said, what is the mummy called? And I looked down here and it said Michael Keaton.
I mean,
definitely not it.
I have no idea.
Oh yeah. It's an Egyptian name.
That does not help me.
I know, you're not going to get it.
Well, then tell me what it is.
Imhotep.
Oh, okay. I do remember that.
All right. In Herbie Fully Loaded, who plays Maggie Payton's father?
Can I get points if I tell you who Maggie Payton is played by?
I mean, who's that?
I think it's Lindsay Lohan, but let me check real fast.
No,
I'm going to check to see if Lindsay Lohan is that. Herbie Fully Loaded?
Mm-hmm. You just use your brain.
Maggie Payton played by Lindsay Lohan.
Okay, great. So who was her dad? Who played her dad?
Oh, Michael Keaton.
Yeah, because you're looking at it right now.
No, because you said it earlier.
Yeah, but...
Because it's not Imhotep, it's Michael Keaton. You think I had time to read it that fast?
Well, you were on it right there.
No, I just saw look at Lindsay. I told you, I knew her name.
Okay. All right. Well, that does it for this week's episode of From Art to Atoms.
The Ultimate Curiosity Show. Thank God.
I know. We're at 2 hours and 15 minutes of recorded time, which, of course, I will
cut down to about 30 minutes.
To about an hour. But join us next week when we revisit an episode that was supposed to have dropped back in the fall, but whoops, I never posted it to Spotify to be released. So we're going to catch up with that one for next week. And you'll hear us discuss all things related to tattoos.
Tattoo.
All right. Have a great week, everybody.
Bye. You've been listening to From Art to Atoms, The Ultimate Curiosity Show, episode number 45. Your hosts are Brandon Shoemaker and myself, Michael Foles. The show is produced by Brandon Shoemaker and is available on Apple Podcasts, Spotify, Amazon Music, or wherever you get your podcast. Be sure to subscribe to this show to stay up to date on all of our latest episodes and news. If you have any questions, feedback, or suggested topics you'd like for us to dive into, don't hesitate to reach out. You can email us at FromArtToAtoms@gmail.com. Also, don't forget to follow us on social media to stay updated on upcoming episodes and behind-the-scenes content. You can find us on Instagram and YouTube at From Art to Atoms, as well as TikTok at _From Art to Atoms. We would love for you to leave comments or likes on our post, and we'll try to give you a shout out on our show. If you enjoyed today's episode, please take a moment to rate and review us on your favorite podcast platform. Your support helps us reach even more interested minds like yours. Thanks for tuning in, and stay curious, everyone.